Assalamualaikum and very good day to everyone. So today we will continue to our new chapter in electrostatic field, which is regarding on the potential difference and absolute potential. So here is our learning objective, okay, which is for this chapter. So the learning objective for this chapter is to enable students to understand the concept of potential difference and absolute potential induced by point charge and continuous charge system. Right, so you will learn about the potential difference and what is absolute potential, right? And also to enable students to calculate potential or potential difference induced by point charge and continuous charge distribution. So here are the two learning objectives that you should able to get by the end of this chapter. Alright, so now let's say we want to calculate the work which is done by a point charge here. Let's say we have a point charge of Q, yeah? Alright, let's say we have a point charge of Q, alright? So this point charge, the charge is Q, alright? And we want to move this particular point charge along this path. Okay, along this path line, yeah, along this path which is from point A to point B. Let's extend the point B, yeah. Let's extend the point B here, right? And at the surrounding or at the environment, there is existence of electric field. Okay, there is an existence of electric field. So when we want to move this particular point charge along this path, yeah, along this path, of course there will be a work has been done. Of course there will gonna be work which is done, right? So let's say we want to calculate the work, a small work done when we want to move the point charge Q along the length, okay, along the length which is along the path, this path, yeah, from point A to point B. So the dW will equals to negative F dot dl. Okay, so you realize that there is a negative here. So what this negative here indicates? This negative here indicates that it is an external work done. Okay, the negative here indicates the work is done by external agent. I try to write it slowly, yeah. External agent, AGENT. Okay, so that's why there is a negative here. All right, it is done by an external agent. Okay, so that this point charge can be moving. All right, so based from what we have learned in Coulomb's law previously, all right, F is equals to QE, if you guys still remember. Okay, so now, all right, so now if we substitute this equation inside this equation, you will able to obtain as such, yeah. So to find the total work that is done in moving Q from point A to point B, so of course you require an integration, yeah. So A will gonna be the initial point or the starting point, yeah, initial point, and B will gonna be your final destination point. Okay, final destination point. Right, so the unit, of course, yeah, the work, the unit will gonna be in a joule. And your DL here, okay, your DL here is based on what are the orthogonal coordinate system that is suits with the structure or in that particular system. So in this slide here, it's just a recap from what we have learned previously, okay, which is the DL based from all the three orthogonal coordinate system, which is for Cartesian is written as such, for cylindrical is written as such, and spherical is written by such. So you have to remember this, okay, because this is what we're going to apply in the equation just now, which is W negative integrations of where are the starting point to the final destination, okay, QE dot product, yeah, DL, okay. Now let's look at the example 1, okay, that I have provided in your slide. So obtain the work. You require to obtain the work done, so you need to calculate the W in moving 2 coulombs. So this is the value of Q. Charge in existence of E. So this is the electric field that is given to us. This is the E field value. Alright. So the first question asks regarding from 200, which is here, okay, 200 to 040 along path 1, okay, along path 1. So this is your initial, okay, this is your initial, and this is your final destination, right? Okay, so let's apply the equation that we have learned before. So 1, so W is equals to negative integrations of starting to n, yeah, the limit QE dot DL. Okay, so we know the value of Q, so Q is not involved, we can bring it in front. So negative Q is equals to 2. Okay, so integrations of E, which is E is given as X hat plus Y hat plus Z and Z hat dot product with the DL. So the appropriate DL that we can use now is you look at your E. Your E has in X, Y and Z, right? So your DL should be in a Cartesian, right? So Cartesian DL we're going to be dx on X plus dy on Y plus dz on Z, right? Okay, so this is all the mathematics, so you can solve this. So x will become 1, so x dx, yeah, integrations of x dx plus, don't forget the bracket, integrations of y dy, okay, plus integrations of z dz, okay. So close the brackets. And now what are the limits? Okay, so limits from x, we look, your x is start from 2, okay, it begins from 2 and it ends until 0, so gonna be 2 to 0. Okay, so that is your limit for x. Limit for y, we're gonna be 0 until 4, so gonna be 0 until 4. And your limit for z, we're gonna be 0 to 0, meaning that there's no changes in your z. So z we're gonna be no changes at all. So if you solve this, you should get, or you're able to get your answer to be negative 12, yeah, negative 12 joule. Okay, so that is the work required, or the work that will be produced if you are moving the point charge from 200 until 040 along path 1, okay, along path 1. Now let's look at question number 2. So question number 2, for this example, they said we still moving the same charge with the same electric field. However, the initial point is still the same. Okay, the initial point is still the same, but the ending point or the final point also will be the same. However, the difference will gonna be the path taken. So now we are using the path 2, which is path 2. If we can see here, it's from 200, it goes to 004 first. Then from 004, it moves to 040. Okay, so this is path 2. So now, in order to solve this, okay, for question number 2, so your work will be, okay, your total work will be, all right, negative, okay, QE dot DL for this line, okay, for this line, which is 1. We can just bring the negative in front, yeah, to make it easier. Okay, I just bring the negative in front and I put some brackets here. Okay, negative, which is along path 1 plus width QE dot DL along path 2, which is this path. Path 2. Okay, and I close my brackets. Alright. So if you solve this, okay, along path 1, it will be, we can bring the 2 in front. Okay, negative 2. So it will be x, integrations of x dx plus integrations of y dy plus integrations of z dz. Okay, and plus, alright, plus with the integrations of x dx again, but this is for path number 2, y dy plus z dz. Okay, alright, to avoid confusion, okay, let's put the 2 inside. Okay, you can also bring the 2 in front, no problem, but to avoid confusion, so this is for the first one, and another one is for the second one. Yeah, I need to add 2 here. Okay, so when how about the limits? Okay, so along path 1, so the limit here we're gonna be from 2 to 0 for x, from y 0 to 0, meaning that your y will be no changing at all. From your z, we're gonna be 0 to 4. Okay, so you can cancel your y because there's no changes at all. And for path number number 2 here, so your x will gonna be 0 to 0, so your x will gonna be no changes, yeah, right. Y will be from 0 to 4, okay, 0 to 4, and then for your z we're going to be 4 to 0. And if you solve this, okay, if you solve this, you will get your answer to be negative 12 joule as well. Okay, you will get your answer to be negative 12 joule as well. So you can see here, actually, if you realize, from the first question with the second questions here at the example, okay, from the first and the second here, no matter path, which path that you are taking path 1 or path 2, okay, you will still get the same value of total work. Alright, so from here we can conclude that, okay, from here we can conclude that, right, if the initial point, okay, if the initial point and destination point, yeah, or final point is same, okay, no matter which part that you are taken, regardless which part that you are taken, the value of work, okay, the work will be same as well. Okay, the total work done will be same as well, regardless any path that you are taken. Okay, alright. So now let's look question number 3. Okay, so question number 3 here, they ask about the round trip movement. Okay, the round trip movement at 200. Okay, round trip movement from 200 along path 1 and along path 2. So what this question mean? They said the point charge is make a round trip which is start from this point 200 and it goes to path 1. Okay, it goes to path 1 and back to the initial point back. Okay, it start from here and it make a round trip. Okay, it make a round trip and it backs to the where it's starting here. So we have calculated just now our path 1, the value of the work here is negative 12 joule, right? It's negative 12. And for path 2, okay, path 2, we have calculated just now from here to here, the value is negative 12 as well, right? So if from here to here, it's gonna be positive 12, yeah? So the work done, yeah, for the round trip movement, okay, so it will be negative 12 joule plus 12 joule, you will get equals to 0. Okay, from 200 to 040, okay, from 200 to 040, it will be negative 12 joule. Okay, it will gonna be negative 12 joule. From 040 to 200, from 040 to 200, it will be 12 joule. Okay, so negative 12 joule plus 12 joule, you will get 0. So from here, what we can conclude is, okay, from here what we can conclude is there will be no work done. Okay, there will be no work done. I just write it as W, yeah. Okay, there will be no work done, okay, in a closed loop. Okay, in a closed loop. So this is like a closed loop, yeah. There will be no work done in closed loop movement, meaning that if, let's say, there is a point charge moving anywhere and then the point charge back to the starting point or back to the initial position back, okay, so no matter how far the point charge travel, but as long as the point charge will be back to where it is started at, okay, there will be no work done. The value of your work will be equals to 0. Yeah. Okay, so from the previous example that we have discussed, so question number 1 and question number 2 denote to us that the work done does not depend on the path taken. Okay, if it is start at the same initial point and if it is end at the same destination point, no matter which path that you are taking, okay, the work done will be same. Okay, work 1 is equals to with work 2. Okay, no matter your path is shorter or your path is longer. Okay, from question number 3, all right, work done per unit charge. Okay, before we said QE, right? QE, and if we bring the Q in front and we bring on the other side of your Q, okay, work done per unit charge, work done per unit charge in a closed movement, in a closed loop movement, right? This is actually a closed loop movement. Closed loop movement is equals to 0, and this is actually our second Maxwell equation, and this Maxwell equation is only true in a static field only. Okay, it only true in a static field, meaning that if your E field, okay, in a static field or in a static form, so your in a closed loop movement, the work will be equals to 0. However, if your E is varying in time, where later we're going to look this, later. If your E is varying in time, okay, so this second Maxwell equation will not be true anymore. So I hope you still remember your first Maxwell equation. Okay, first Maxwell equation tell us about the divergence of D. Okay, the divergence of D is equals to rho V, right? So the second Maxwell tell us divergence of cross E is equals to 0. Okay, if you want to write in this form, then it will gonna be, so it can be able in two form. E dot dl is equals to 0, and this one is gonna be d dot ds is equals to q enclosed, which is equals to rho v. Okay, equals to q enclosed, or it equals to rho v. Okay, now let's look at the another example that I has provided in your slide. Example number 2. So the electric field intensity, so the E field, in free space, okay, in free space is given by as such. So let's look, or let's get some information from this electric field. We can see it is in a x, y and z direction, meaning that this is in a Cartesian. Cartesian coordinate, and what we need to calculate, we need to calculate the amount of work. So we need to find W to move a 2 micro, so this is the value of Q, 2 microcoulomb charge from 211. So this is the initial, I put it as I, and this is our destination, final 512. Okay, so let's try to solve this. So W is equals to negative QE, right? QE dot DL. Okay, dot DL, and we can bring the Q in front here. The Q is not involved in the integrations, so Q, so left behind the integration is E dot DL. Okay, and we know the DL is in Cartesian. Okay, so DL in Cartesian will gonna be in dx on x direction plus dy on y direction and plus dz on z direction, right? Okay, so the value of q is given as 2 micro. Okay, your E is given as 2x y z on x plus x squared z y plus x squared y on z direction. Okay, dot product with the dl, so gonna be dx on x direction plus dy on y direction plus dz on z direction. So we can proceed our calculation. So the integration will gonna be for x, okay, 2x yz on dx plus x squared z dy plus x squared y on dz. Okay, don't forget to write the bracket there. So what are the limits? Okay, so the limits for x are gonna be from 2 to 5. 2 to 5. For y, 1 to 1. So we can see there's no changes, right, in y. So y is gonna be 0. From z, it's gonna be -1 to 2. Okay, and try to solve this. Try to solve this and you will get your answer, and it's supposed to be in a joule. Alright, so thank you very much and see you in our next lecture, which is regarding on the potential difference and potential.